So good afternoon everyone. Today I'll be sharing with a video. We'll be continuing where we have left in the last class. That is the interconversion of states of matter. Here we'll be discussing how one physical state, you can say solid, converted into liquid, liquid to gas. Gas can be converted directly to solid. What is latent heat of fusion, latent heat of vaporization? What is the relationship between Kelvin, Celsius, Fahrenheit? So just please go through this video properly before attending today's class, and we'll be sharing this video in the class also.
Let's say we want to go from liquid to gas, or maybe from gas to liquid. So what is the way that we can change the state of matter? So very good. I see some of you are writing heating or cooling, or by heating, right? Melting it, heating it. So melting is the term here, but what are we doing? That's right. So we are heating or cooling the substance, right? So can we say that we are changing the temperature? So one way is to, so if we categorize it, we can say by changing the temperature, right? So all of you know, by heating or by cooling, we can change the state of matter. So we can say by changing the temperature. Very good. Guys, is there any other way? So is there a second way to change the state of matter? So one way is just changing the temperature. Very good. I see Darkshit has written by change of pressure. Excellent. So the other way is to change the pressure. So please remember these two very important points. Very good. I see by applying pressure, a lot of you are writing. Excellent. That's the right answer. So remember this very important point. How can we change the state of matter? By changing the temperature or by changing the pressure. And we are going to be discussing both of these in this important video. Okay, so as we said, so let's talk about the first way, by changing the temperature, right? So we can go by, so if you look at this, so if you go this way, by increasing the temperatures. So note here, the red arrow means increasing the temperature. So by heating. And the blue arrow means cooling, right? Can you see the blue arrow here? So that's decreasing the temperature, right? So let's start with this simple example. Let's say we are going from solid to liquid. So as you guys know, to go from solid to liquid, we need to heat it. Now, what is this process or this conversion or this change of state known as? Guys, can you tell me? So what is the question is, what is the process or the change of state from solid to liquid known as? How do we do it? By increasing the temperature. But what is it called? Excellent. Some of you are writing melting, fusion, right? No, we've not come to latent heat of fusion as yet. So this is just the simple thing we're talking about, the change of the state, right? So the process is known as fusion. Or another term is melting, right? So to go from solid to liquid, you need to do fusion or melting. So as you can see from this picture here, so for solid, we have the example of ice here, right? And liquid is water. And guys, can you see the gas over here? So that's steam or water vapor, right? Okay. So as you know, so to go from ice to water, if you take that example of solid to liquid, the process is known as fusion or melting, or for any substance, right? So going from solid to liquid is fusion. Now, can you tell me what is the process from going from a liquid to a gas known as? Okay, so we're looking at this, this process here. So let's say we want to convert the liquid to a gas. So if you consider the example, we want to convert water to steam. So guys, can you tell me what is this known as? Excellent. Some of you are writing vaporization, boiling. Some of you are writing evaporation. Be careful. Evaporation is not the correct answer here. Evaporation is a separate topic which we will not talk about in this video. I actually have a video on that, so you can check that. This process is known as vaporization. So vaporization, or also some of you have written known as boiling. But the more common term is vaporization. So guys, going from liquid to gas is called vaporization or boiling. note, don't write evaporation here. That's not the correct answer. And I'll try to talk a little bit why later in the video. So please remember these important terms. Now let's look at the opposite thing. So let's say we have reached the gas state, let's say steam, right, or water vapor, and now we are decreasing the temperature, okay, and we are coming back. So we know that by doing cooling, we can go from gas to liquid or steam to water. So guys, can you tell me what should I write here on the blue arrow? So what is this known as? Okay, so can you tell me from gas to liquid, what is it known as? Excellent, superb. I see a lot of right answers here. So you are saying the correct answer is condensation. That's absolutely right. So going from gas to liquid, the right answer is condensation. You guys rock. That's the absolutely right answer. Now let's take a look at going from, let's say we are at water and we are converting to ice here, right? So going from liquid to solid. So what is this known as? And note, you might find different terms in different books, okay? So I'm using the most commonly used term. So yes, some of you might find your book having a different terminology. So it's fine, you can use that, but this is the most common terms that we are talking about. So what should I write here? Some of you are saying solidification, some of you are saying freezing, right? Okay, absolutely right. So this one is known as solidification or freezing. Okay, so please remember these important terms, and as I said, you might find different terms in your in different textbooks. Okay, so excellent. Please remember this important chart, and you can copy it down after the class or take a screenshot, right? So this is very important to know these terms. Okay, now let's talk about melting, or what we call as fusion, right? So as we saw in melting or fusion, we are going from ice to water, right? So that's an example. So going from solid to liquid. So when you're doing melting, you're heating it. And there's this important term here known as melting point. What is the definition of melting point? The temperature at which a solid substance melts and changes into a liquid at atmospheric pressure. Okay, so this all of us understand, the temperature at which the solid changes into liquid. And as we discussed, you can change the state by changing the temperature or pressure. So it's important here to specify that we are doing the experiment at 1 atmospheric pressure or at the normal pressure. So all of you right now are experiencing the normal atmospheric pressure. So we've specified that, and we are saying if we consider the pressure as 1 atmosphere, at what temperature will it melt? So let's consider this example. So what do you think at 1 atmosphere? So here's our question. What is the melting point of ice? So at what temperature does it melt? Can you guys tell me? So good, I'm seeing some answers here. Right? So what is the melting point of ice based on this definition that you see here? So 0 degrees Celsius, very good, right? So I think all of you know that the melting point of ice is 0 degree Celsius, okay? And I see some of you are writing the answer in Kelvin, very good. So as you may know, that temperature, there are 2 important units. Actually, there's Fahrenheit also. So, but the important ones are degree centigrade, right? So you have degree Fahrenheit. And please remember, Kelvin, don't write the degree. You just write capital K, okay? And how do we convert from centigrade to Kelvin? So what's the conversion? You add 273, okay? So, or it's actually 273.15 or 273.16, but we'll just roughly say we add 273. So this is the melting point of ice. 0 degree centigrade or 273 Kelvin. Excellent. That's the correct answer. You guys got it right. Very good. Remember that value. Okay. So now let's visualize this melting thing based on the, so here we were just showing the ice and water picture to you, right? But now if you take a look, we are now looking at its molecular structure. So let's take a closer look what's happening here. So the temperature we know at the melting point, it's changing from a, so as you can see here, from a solid to a liquid. Okay. And guys, can you see in the solid, can you see that all the particles are tightly packed? Okay. So you know that in a solid, the particles are tightly packed and they are just vibrating about their mean position. right? They have less kinetic energy, there's strong force of attraction. But if you compare it with a liquid, right? Can you see? So here we can say the particles are very tightly packed here. And here they are more loosely packed. Can you see that? So they're more loosely packed and they are moving with more kinetic energy, right? So what are we doing when converting from a solid where you have all these tightly packed particles to a liquid? Basically, you are using the heat energy to overcome the strong forces of attraction. Very good. Somebody saying intermolecular forces of attraction. Absolutely right. So we are overcoming the forces of attraction using the heat energy, right? And that's how we cause the solid to change to a liquid state. So look at this visualization. This is very important for you to understand at a particle level what's happening, right? So the solid here, can you see the tightly packed particles are on heating, changing into a liquid, where they are more loosely packed and they have more kinetic energy. They're moving more freely. Okay, so very good. And as you know, the solid which had a fixed shape and volume, it loses that fixed shape in a liquid. And so we need to use a container to store it. So it takes the shape of the container, but the volume is remaining the same here, right? So excellent. So the liquid has a fixed volume. I shouldn't say volume is remaining the same. Sorry, the liquid has a fixed volume, but it has no fixed shape, whereas the solid has a fixed shape. Okay, very good. Now let's go on to boiling. Okay, so boiling, you know, as we discussed, boiling or vaporization, you're converting the liquid to a gas. So what is the definition of boiling point? The temperature, right? That temperature at which the liquid boils. So the liquid boils and changes into a gas, again at atmospheric pressure, or we say 1 atm, 1 atmospheric pressure. So we don't want to do the experiment at double the pressure, like 2 atmosphere or 3 atmosphere. We are defining it at 1 atmospheric pressure. Okay. And now can you see this visualization, what's going on? So what do you guys notice when you're going from liquid to a gas? Okay. The particles are moving more further away, right? There's less intermolecular attraction and they are moving with more kinetic energy. So this is what boiling or vaporization does. The heat energy is again used to overcome the forces of attraction. You're basically pulling away the liquid molecules and changing into a gas. Okay. Oh, and great. Before even I ask the question, you're ready with the answer. Excellent. So the question is, what is the boiling point of water? Very good. And don't forget to write the unit, guys, right? Some of you are writing 100. It's the right answer, but you need to write 100 degree centigrade. Okay. And as we know in Kelvin, we need to add 273 or 273.16 to be correct. But I'll just add 273. So it's going to be 373 Kelvin. And please don't write degree for Kelvin. That's a very important point. So for degree Celsius, we write the degree here, but Kelvin is just 373 K. Excellent, guys. That's the right answer. Okay. So this is what we talked about, the boiling point of water. Now, of course, different substances will have a different boiling point. Now let's look at this interesting thing. What is the temperature change that happens when you heat water? So please listen to this part very carefully because there's something really interesting going to happen here. Okay. So here, as you can see in this picture, we are taking the example of, let's say this is water here. Okay. And using this burner, we are heating the water. And here I have a, can you see this? Thermometer is dipped in to the water so that we can measure the temperature. Okay. Now we are going to measure the temperature, the rise in the temperature. What's going to happen in this thermometer as we keep on heating the water? Okay. Are you following me? And let's say the water is, so when we start heating the water, let's assume the water is initially at 20 degrees centigrade. So the initial temperature of the water is, let's say, 20 degrees centigrade. Okay. So that's when the time starts and we start heating. So we've taken water at room temperature and we are going to heat it, right? So let's say this is 0 here. And the time is going to take, right? So I'm just going to write some rough values here. Let's say the time is in minutes. Okay, so these are just rough numbers. So after 1 minute, after 2 minutes, 3 minutes, 4 minutes, and so on. Okay, and as we said, the temperature of the water, the starting temperature is 20 degrees centigrade here. So these are all in degrees Celsius. Okay. So now when we are heating it, as expected, what do you guys think? So when we heat the water, will the temperature rise? Right? So yes, the mercury level is going to rise here. As we start heating this water, the temperature is going to rise. Let me just draw the graph again for you. So the temperature is definitely going to rise. Okay. And the rise will continue for some time, right? So it'll keep on rising, it'll keep on rising. And what do you think? Will it just go on rising? Now, a very interesting thing is observed that after some time, the temperature rise stops. So it goes on rising for a certain time, and then it becomes flat for some time. Okay, so this is done by doing an experiment, right? It's not what we are trying to guess here. If you do this experiment, this is what you're going to observe. And then as you keep on heating, again, you'll see a rise here. And so what they observe is that the temperature, this flat line we saw, when it remains flat, is at 100 degrees Celsius. Okay, so yeah, the rise stops at 100 degrees centigrade. So this is very interesting that when you're heating the water, it's going, let's say, from 20 to 40 to 60, 80, right? It keeps on rising initially. So can you see that in the graph? The temperature keeps on rising. And then let's say after around 2 minutes, it becomes at 100 degrees centigrade, right? It doesn't rise further. And that's what's shown in the thermometer. So it stops at, let's say, so the level here becomes 100 degrees centigrade where it stops. Okay. And then if you keep on heating, then at 100 degrees centigrade, as we said, what's happening here? The water is turning into water vapor, into gas, right? Or what we call steam. So the water, the liquid is changing into gas at 100 degrees centigrade. So we can say over here that the change of state, okay? So the change of state is happening here. And this is very interesting that when the change of state is happening from liquid to gas, there is no change of temperature. So if there's one thing you want to remember from this class, this is the most important thing, that during change of state, there is no change in temperature. Can you see that, the flat line? And once the change of state happens, so once it entirely changes to steam, right? Then it into a gas state, then it starts increasing again. So it's going to go 101, 102, 103, and let's say it's 110 here or 120. So it'll keep on rising if you keep heating it further. Or probably if it's an empty container, all the gas will go out, right? So this is a very important concept that during change of state, okay, please note this important thing, during change of state, no change in temperature. Can you see that? And this is experimentally observed. Very, very important point, and we're going to discuss why. So very interesting. Yeah, I know some of you are asking, why is this happening? So let's try to understand why. Okay. So the key thing, the key term here is called, that's right, it's called latent heat. Some of you are writing. So let's first understand what is water, what is the heat doing when it's going from 20 to 100. Okay. So in this part, when you're heating it, it's basically increasing the kinetic energy of the molecules. So in this part, all the heat is being used. So heat is used to increase the kinetic energy. All right, KE for short. So increase the kinetic energy of the particles. They're moving faster and faster, and the temperature measures the average kinetic energy. But once you reach 100 degrees centigrade, all the heat energy, as this slide says, is used to overcome the force of attraction, right? So then the heat is not interested in increasing the kinetic energy. It says you reached 100 degrees centigrade. Now I'm going to start changing your state, right? So the entire heat is being used to overcome the force of attraction, because as you can see from this picture, from liquid to gas, it needs to, the molecules are further away. It's breaking those intermolecular forces and changing it from a liquid to a gas, as you can see here, right? So it's changing from liquid to gas. So the latent heat is used to overcome the force of attraction, right? And this is the important point. The kinetic energy is not increasing, right? So kinetic energy does not increase here. And that's why the temperature, there's no show of rise in temperature, right? Kinetic energy does not increase. All the energy is spent in changing the state to overcome the force of attraction. Clear? And that is why this is known as latent heat, right? So why this term latent heat? So latent means hidden, okay? Because we are saying that, because as you can see, the burner is on here. So can you see? You're still heating it. It's not that you switched off the gas or the burner. It's still on. You can see heat energy is being consumed. Heat energy is being supplied, but it's called hidden because why? We cannot see it. We cannot observe it in the thermometer. So it's all getting hidden into the substance to change the state. And that's why it's called latent heat, hidden heat, because the heat that's being added cannot be observed in the thermometer. The kinetic energy is not changing and it's only being used to change the state. Excellent, guys. So please remember this important concept of latent heat. And we call this latent heat the latent heat of vaporization. Because what is the change of state going here? As we discussed, so when we are going from a liquid to a gas, right? It's called vaporization. So this is known as latent heat of vaporization, right? And what is the definition of it? The quantity of heat, right? That is used to convert 1 kg. So we are saying that because obviously if you take more water, you need more heat. So we are fixing it to a unit mass, right? And the SI unit is kg. So we are saying unit mass, that means 1 kg if we take, and we need to convert it from liquid to gas, right? Can you see that? It's written here. So converting to liquid to gas without any change in temperature. Because during change of state, there's no change of temperature. So without any change of temperature, how much heat is needed? And that is called latent heat of vaporization. And in some books, you might also find this term written as specific latent heat of vaporization. So specific latent heat, okay, of vaporization. So it depends on what book you're using. So these are the terms, right? So, and it's given a definition. Now one question is, do you know what is the value for water? So what does this mean? That guys, if you take 1 kg of water, how much heat energy, right, is required to convert from liquid to gas? And we know this is all happening at 100 degrees centigrade, right? 100 degrees Celsius. Okay. So guys, do you know what is the value for water here? So how much latent heat is needed? And you know what is the unit of heat energy? Right? Excellent. I see that some of you are writing the correct answer. So what is the unit of, so here the value is 100 degrees centigrade is the temperature. But I'm asking what is the latent heat of vaporization or the specific latent heat? Because what is its definition? The amount of energy needed to convert 1 kg from liquid to gas. Okay. So yeah, it's measured in joules or kilojoules. So the value is 2260 approximately again kilojoule per kg. Why we say per kg? Because we are taking 1 kg. So obviously if you take 2 kgs, you need to multiply this value by 2. So the unit is defined as kilojoule per kg, or this you can write it as 2260 into 10 to the power 3 joule per kg, right? Kilojoule is 1000 joules. Okay, so guys, can you see that? So you need to remember this value. Yeah, in some books you might find a little different value, but this is the rough average value for changing the liquid from water to gas. And this is the amount of energy that's needed. Okay, so it's useful to know this value. Okay, very good. So guys, here I want to ask you, what do you expect? We discussed of the simple example of water, right? Because you know that when you're, let's say, making tea, right, you boil water. So this process we are familiar with, right? Changing liquid to gas, and you can, if you do this experiment with the thermometer, that's what we observe, right? So as we discussed, we observe this graph here. Now the interesting question is, what do you think is going to happen when we heat ice? So let's say we take ice here. So guys, can you see this ice over here? So this is the ice here. And same thing, when we heat it, will we get a similar graph like this or no? What do you guys think? So my question is, we saw this graph with the familiar example of liquid to water, to gas, right? And now if we do from, we start heating ice, okay? So what do you think we're going to observe here? And let's say the ice we've taken out is at, initially it's at minus 10 degrees centigrade, okay? So let's say this ice is at minus 10 degrees Celsius, okay? So again, we can say the time is in minutes, and So these are, of course, just rough numbers. Let's say we have 5 minutes here. And so this starting point is at minus 10 here. So this is minus 10. There's a 0. Right? So let's say here's the 0, then 10, 20, and so on. Right? So will we get a very good? A lot of you are saying the same graph. Absolutely correct. Excellent. So that's the right answer. So when you start heating the ice, let's say you took it out from the freezer and it's at minus 10 degrees centigrade, okay? And you start heating it, again, the temperature is going to rise, okay? And then where do you think it's going to become flat? As we discussed, when the change of state happens. And that's going to happen at 0 degrees centigrade, the melting point of ice, right? There it was the boiling point of water. So here it's going to happen here. And till all the ice is melted, it's going to stay 0. And again, it's going to keep rising. Okay, guys? So this is the very important thing. And as you can see here, this is where the change of state is happening. So where the ice is melting. And can you see it's happening at 0 degrees Celsius. Okay? So very good. It's exactly the same graph. And as we said, when there's a change of state, there's no change in temperature. Only once all the ice has converted to water. So this is very interesting. It waits for all the ice to convert to water, and that's when the temperature starts rising again. So please remember these very important concepts, and then you'll find the chapter really simple. Okay? And so again, you can see the latent heat is doing what? So here, why again it's called latent heat? Because we don't observe any change in temperature in the thermometer during this change of state. So again, it's known as latent, which means hidden heat, right? So this is the hidden heat. And it's again being used to overcome the force of attraction, because you know that in a solid, the force of attraction is more than in a liquid. So it's tearing away the molecules. Can you visualize that? It's pulling away the molecules and making it melt. So as you can see, it's changing the state from solid, so from the ice to water, liquid here, right? And again, the kinetic energy is not increasing. It's using it to overcome the force of attraction, and all the heat is being used to change the state. And because we cannot observe it, you don't see any change in the thermometers. Where's all the heat that we are supplying going? So can you see we are supplying heat here? It's hidden. And that's why it's called latent heat. Great. So are you clear about the concept? And just like there it was called latent heat of vaporization, here it's going to be called latent heat of fusion. So you guys can take a look at the definition. Same thing. It's exactly the same. You're using, let's say you're taking 1 kg of ice, right? So 1 kg of the solid. In this case, it's ice. And when it's changing from solid to liquid without any change in temperature, then that heat is called latent heat of fusion. And guys, do you know what is the value for ice? It's okay if you don't know, but you need to, it's good to learn these values, right? So there we had seen what is the value here. For latent heat of vaporization, it was 2260 kilojoule per kg. So is it that same value or is it a different value for ice? What do you guys think? So what is the value of ice, the latent heat of fusion for ice? Does anybody know? Okay. So this value again, it's an approximate value which you should learn. It's 334 kilojoule per gram. What does that mean? That if you take 1 kg of ice, right? We need to supply, how much heat is being supplied here? 334 kilojoule, which is basically 334 into 10 to the power 3 joule per kg. Can you see that? And as we said, this can also be known as specific latent heat or latent heat of fusion, right? So it's specific because it is for 1 kg, right? So please learn this value, and as you can see, ice needs less heat to go from 1 kg of ice to 1 kg of water. It's 334 kilojoule per kg, but steam actually needs more. It needs 2260, right? Can you see that? So it's not the same value. It's not that for every change of state, it'll be the same. It's a different value. And obviously for different substances, it's going to be different. Okay. So is that clear? Excellent. So now one very interesting question we have, that can solid change directly into gas? So as we saw here, here's the summary, right? We saw that solid can change to a liquid, that's known as melting or fusion. Then liquid can go to gas, which is known as vaporization or boiling. And then if you decrease the temperature, it's called condensation. And this one is known as freezing or solidification, right? Okay. So very good. A lot of you are answering that. I see the correct answer. Absolutely right. So what is the answer? It can go, and this process is known as sublimation. So excellent. So sublimation is a very interesting thing where when you heat a solid, it just skips the liquid state. Okay. So it doesn't go to the liquid state. It directly, can you see the arrow? It directly jumps to the gas state. So let's say this is a solid. It directly goes into a gas state. And that process is known as sublimation. Excellent. That's the right answer. So remember this important term. It is possible for a solid to go to gas. And that's called sublimation. Okay. So guys, do you know, so you need to learn the important substances that show sublimation. So I have a question here for you. So which out of these substances, so let's go one by one. Do you think sodium chloride is an example of sublimation? So let's go one by one. So first we are talking about sodium chloride here. So does that show sublimation or no? Some of you are saying yes. Naphthalene, very good. So some of you already answered for this one. So that's absolutely right. Naphthalene is an example of sublimation, right? Because we use that to make sure the clothes don't get spoiled, right? Camphor is another very good example. Excellent. Now let's take a look. What other things did you see here? Dry ice, very good. So do you guys know what is dry ice? Dry ice is a very interesting thing, right? So what is dry ice made of? Camphor, very good. I'll add that to the list also. So you guys have given another example here. Excellent. So camphor shows sublimation. Very good. And dry ice is carbon dioxide. Very good. Or we normally call it solid carbon dioxide because it is solidified form of carbon dioxide. So just like we freeze water to get ice, if you take carbon dioxide gas and freeze it to make it a solid, it's called dry ice. Now, why is it called dry ice? Because when it sublimes, okay? So when dry ice changes, so look here, so let's say this is dry ice, which is solid carbon dioxide. So when it changes or when it sublimes here, it directly changes to carbon dioxide gas. It skips the liquid state. So it doesn't melt. It directly becomes the gas, and that's why it's called dry ice, because it doesn't cause any wetness, right? So it doesn't go through the liquid state. Okay, so dry ice is an excellent example. What other things here, guys, do you know? Okay, so iodine is also an example, right? And ammonium chloride. Okay, so what is not an example here? So don't confuse. So sodium chloride is not an example of a substance that sublimes, and chlorine is also not an example. So chlorine gas is not, right? So for example, if you take sodium chloride, ammonium chloride, the sublimation can be used to separate these two salts. You know that sodium chloride is the salt that we eat. Ammonium chloride is also another salt. And so we can use the process of sublimation to separate them, because ammonium chloride will sublime, but not sodium chloride. Okay, so remember that. That can be used as a useful way to separate these guys. So it's good to know a list of all the substances that sublime. Okay, excellent. Now, one interesting question is the reverse also possible? So can it go from gas to solid, right? So if you heat dry ice, it becomes carbon dioxide. So can we go from gas to solid? So can we do this, right? So is this possible, and what is this known as? So can a gas directly change back to a solid? So a lot of you are saying yes. And so what is that process known as? So we know the process below is called sublimation, right? So going from solid to gas. So what is going from gas to solid known as? So what do you think, guys? Yes, it's possible. And the process is known as, again, the same name, sublimation. Again, you might find some different terms in different books, right? But usually this is a little confusing because we say going from solid to gas is called sublimation, and the reverse is also called sublimation. So the carbon dioxide, for example, can be converted into the solid, or if any substances that can be converted from a gas to a solid directly, that process is also known as sublimation. So here's the entire summary that you can see here, right? So we did from solid to liquid, that was called melting or fusion. Then we had boiling or vaporization, then condensation here, and then freezing or solidification, right? Solidification was liquid to solid, and then we have these important things going from solid to gas, or gas to solid is sublimation. So please remember this important summary. I put it there for you, and you can see that visualization of the molecules, right? In the solid, can you see they're all tightly packed, and when you heat it, they become less tightly packed, it changes into a liquid and then into a gas. Okay, so is that clear? Right, so please remember this really important summary. And remember, in the initial part of the class we talked about, so one way is to change the temperature, right? And the second way is to change the state using change of pressure. Okay, so this is one important thing that we sometimes forget, right? So one important way is to change the temperature. The other way is using change of pressure, right? So guys, can you give me an example of a substance that shows change of pressure? So can you give me an example of a gas that can be liquefied here? Can you see that? So gas that can be liquefied by increasing the pressure and decreasing the temperature. Okay, so what we do here is that if you compress a gas, right? So let's say we apply a lot of pressure here. Okay, let's say a lot of pressure is applied here. So you can actually, so when you apply the pressure, right? So when you're applying pressure, you're basically getting the molecules closer and closer to each other. So can you see in the gas here, the molecules are further away. But in the liquid here, you can see that the molecules are much closer to each other. So by applying pressure, we are getting the molecules closer to each other, so we can cause a change of state. And sometimes we also, so excellent, I'm seeing a lot of good answers here. People are saying LPG, CNG, carbon dioxide, right? Ammonia is another good example. So excellent. So yes, we can apply this for many things. For example, you have the LPG gas, the CNG, and ammonia is another good example of something that can be, ammonia can easily be compressed, right, into the liquid form by applying pressure. And we also decrease the temperature so that we don't have to apply too much pressure, right? So both factors are helping in changing the state. And we call this process known as compress and cool, right? So you're compressing the gas and cooling it. So both the things, you can see that when you apply pressure, you're getting the molecules closer to each other. So the state is changing from gas to liquid, and also cooling is bringing the molecules closer to each other, right? So that's how we change it. Very good. And some of you are saying that's how we get liquid nitrogen.
So with this, we can understand what are the impacts are happening. Okay, we'll be discussing also. So